chemistry you've got tomorrow, or the math on this, then we could just end it early. But I thought it'd be good to sort of check in and see how everyone's doing, because I think debriefs are always best when you're sort of fresh and just come out the paper, because then you're like, oh, you remember what all the questions are, you remember if some of them are really ugly, you remember if some of them are really nice. And so, yeah, I just wanted to pop on and see if anyone sort of had any chat or any questions, really. So as always, when it comes to the sort of debriefs where it relies a lot more on the chat, it's a lot more of me filling space while I wait for people to sort of populate, see if anything kind of comes up. So in the meantime, let's kind of talk about like what the paper 3 was, right? So to the experimental physics, because that's the one. With 1 and 2, you kind of know what you're going to get. With 3 is the wild card. 3 is the tricky one. But from what you guys said, for those of you who are in the Discord, apparently paper 3 was good for some. Controversial. Good for some, decent for others. And I'm seeing another comment saying it wasn't suited to your particular style. And that's kind of the way it works, right? Is with the paper 3, it depends very much on which topics come up, which experiments come up, whether you like them, and exactly what they ask you to do with the data. So that can be really tricky. Also, like I remember you guys were complaining a lot about the math paper 1. That seems to be like across the board complaint. Like I've seen YouTube videos going through it where the thumbnail is like hardest A level ever, and just like really, really, really tricky. I have actually seen that paper. Someone managed to, I don't know how, what sort of witchcraft they used, but they managed to get a photo of it, like or some sort of scan of it and send it to me. So I've had a look at it, and it definitely was difficult. But yeah, so you guys have done physics. Apologies that I couldn't do a specific recent paper 3 live stream going through the experimental, but I definitely had the sort of past streams. I've done a past paper 3 live solve, and I talked about experimental physics before. So hopefully you guys found that helpful if that's the kind of thing that you needed in the final stretch going into this paper 3. But now looking ahead, so math paper 2, sort of strategizing while I wait for people to sort of warm up the chat. Strategizing for paper 2, given how difficult paper 1 was, for a lot of people, you're going to be feeling this increased pressure when it comes to paper 2 and paper 3, especially if you're doing EdXL, which was the really tricky one. So top recommendation there would be making sure that your exam technique is really on point, that your checking technique is really on point, and that you're getting every mark you deserve so that you're climbing higher up that curve, right? So it could be that paper 2 will be easier to compensate for the more difficult paper 1. And if that's the case, excuse me, if that is the case, then you're going to have to capitalize on all those marks. So little small mistakes might be more costly than they would have been otherwise. So definitely something just to bear in mind. I'm also going to keep carrying on with the OCR MEI paper 3 solves, just because I think there's less to do with that. Oh, hello, we got chat. Paper 3A had internal resistance. Love that. And I really hate how in the formula books they have the form epsilon equals I into brackets big R plus little r. I hate that form because V equals epsilon minus IR is the one that you can actually plot on a graph based on stuff that you measure. So I'm assuming that's what will have come up if it came up in a practical physics. So internal resistance came up. Oscillations, love that. I'm hoping sort of measuring from the equilibrium position, so there's less uncertainty in the time period. Taking 10 oscillations and then dividing by 10 to decrease the uncertainty in the time reading of the period, that kind of thing. Radioactivity. I wonder what came up with radioactivity. Was that talking about, for instance, sorts of like random error, the fact that it's a random process? I suppose you could talk a lot about safety when it comes to the radioactivity. And acceleration due to gravity. Okay, so lots of questions there. Were there any challenging ones? Were there any proper difficult ones? Nothing specific happened in the Discord server about it. So I don't know any of the specific questions, whether they were particularly tricky. Because I will say that AQA seemed to have sorted their game out, because I know for a few years there, every single paper was like diabolical, like so bad. Hello, hello. So yeah, like a lot of the papers were really, really bad and were like genuinely not giving people a chance to demonstrate their ability. And so it's good that they seem to have leveled themselves out. Like paper 1, paper 2, I don't remember hearing much complaint about the physics. The only paper this season that people have really complained about is that math paper 1, which I think is a good sign. Well, pros and cons. I mean, the math is the one that most people have demands for an A star in. So it's a little trickier from that perspective, but it seems that a lot of people were on lock and did a really good job in the physics. So I'm definitely happy that you guys had that experience, and hopefully that comes through for you in results. You got a 6 marker on OCR's paper 3 about a balloon on Earth and a balloon on Venus. Interesting. Earth had hotter air inside, and Venus had a lower mass gas. Oh, wow. Density and forces. So the forces, obviously the gravity will be different. That's weird. That's really outside the box. Maybe I should be having a look at these OCR paper 3s. So you can obviously, so the density of the gas will obviously impact the mass of the gas. But then the G will be different, so that'll impact the weight. What was it asking you to consider? Was it saying which one would be bigger at atmospheric pressure, or how the forces would balance? Genuinely, I'll be curious to get into that when it becomes available. Oh, yeah, someone's saying there's a lot of how a graph would change after a change to the experiment. Those can be really tricky, because it's very easy to understand that they change, but it's not necessarily easy to understand in which direction, where you kind of have to think, all right, if that was bigger, then this would be bigger, then that would be smaller, then that would be smaller, and that would impact the y coordinate this way. Like, it could be really difficult to thread the logical needle there. Yeah, I'm hearing that. I'm hearing that OCR was weird. OCR was non-standard. I think AQA was okay. I really want to get into this balloon question. It was just explain how they stay at a constant height. That's interesting. I kind of want to get into that. Let me get the whiteboard open. Let me move that over there. Let me get the whiteboard open. I want to consider that. That looks fun. So how they stay at the same height is because, well, if they're not, that implies they're floating. That implies they're not moving. And they would not be moving. That implies the forces are balanced. So you need to consider what the forces are. Pressure would be the same in all directions. So you don't really need to consider the force due to that. What I'm thinking is you need to consider, if I just park you guys over here for a bit, it seems to me that you would need to consider upthrust versus weight. So if we've got a balloon, the upthrust is equal to the weight of the air displaced. So that would be the density of the atmosphere times the volume of the balloon. And the force down would be times G of the whatever G happens to be for that planet. Whereas going down, it would be the density of the gas times the volume of the balloon times the gravity of the planet. And so actually, I think it shouldn't depend on G, because that will affect the upthrust and the weight proportionally, and kind of same with the volume. So it seems at first glance like it would only depend on the density of the atmosphere versus the density of the gas. But maybe I'm oversimplifying this. Explain how they would stay at constant height. I suppose you can get into the whole Newton's laws of it all. So if it's staying at constant height, then that means the velocity is 0, Newton's first law says that an object stays at rest if there's no net force acting. So there's no net force acting. Newton's second means that the resultant force is zero. You consider the forces, you say they have to balance. I think it actually doesn't seem to depend on anything other than the density of the density of the outside atmosphere and the density of the gas in the balloon. So based on your initial question, Earth had a hotter air inside and the Venus one had a lower mass gas inside the balloon. Unless I'm missing something. I'm so interested now. Oh, so it had like a table with different temperatures inside and outside the balloon. And the mass of the gas inside and outside the balloon, you got given a bunch of values. Oh. That does not look fun, guys. Because also gas laws, there's so many little variations, especially when you get into the kinetic theory equations as well. I would not have enjoyed that. I wonder if I can get into it. So there's temperatures inside and outside. And I don't know. I'll wait for more information to come in about that before I do a deep dive. In the meantime, let me catch up with some of the chat. So pre-OCR non-standard. You said MGH equals rho GV. Surely you don't mean MGH. Surely you mean MG, the weight equals rho GV. And you found the 4 densities required. Okay. Someone's saying astrophysics had a question on if you could see 2 craters and the diameter of each crater was less than the minimum distance you can see from the telescope, but the distance between them was greater. So you would be able, in that case, so this is about sort of Rayleigh's criterion, resolving power of telescopes. You would be able to resolve them in terms of their separation, but I don't think you would be able to see them even if they were on their own. You wouldn't be able to resolve that there was a crater there, regardless of whether the separation between them. That's interesting. So that's quite edge case. Hello. Someone saying they're an Indian student. Often watch my videos. Help them for some of your papers too. Yeah. Yeah, throw it in. Throw the question in. Let's see if I can do it. Because at a certain point, math is math and physics is physics, right? So your ability to get your questions answered will help other people invite, like so on. All right, so we got someone else saying, did AQA paper 3 today, and it was in some insight into the resonance graph of a mass spring system. Okay, so all right, let me get into that. Right, so we've got mass spring system. You've got the resonance curve. Interesting. Do I know how to do that off the top of my head? Let me have a think. So I know the resonance curve is certainly, I can see what's going to happen. So, okay. So if we've got a mass spring system, let's think about what for a second here. So we know T equals 2 pi root M over K. So what we know is that F is equal to 1 over 2 pi root K over M. So if it's half the mass, then F2 would be 1 over 2 pi root of 2K over M1. So in other words, it's root 2 times the first frequency. Now, remembering that resonance happens when the driving frequency is the same as the natural frequency, this means that the driving frequency would need to increase by a factor of root 2. So if we think about amplitude versus frequency, If the initial peak is something like that, then the other peak would be something that like would happen over here, sort of root 2, factor of root 2 in it. That's what I'm thinking. Could not figure out the max amplitude. Well, the max amplitude, though, is that something you actually have to work out? The specifics, like how it would impact the maximum amplitude. I know you have to think about, because that the maximum amplitude depends on damping forces, for instance, and things you might not necessarily have. They just said draw on the figure. It may be that that the question was not really asking about amplitude, so it may be that you get away with that. That might not be where one of the marks is available, so you could be completely fine on that. I definitely. Do I want to have a go? I will come back to. I do want to have a better crack at this one from the OCR because that looks really interesting, and I don't know how to do it off the top of my head. Let me. Oh, it was also more heavily damped, and not just half the mass. Well, if it was more heavily damped, then the amplitude would be lower. So it might have been qualitatively that the amplitude is lower if the damping is increased. So you may not have needed specifics, maybe just a range. Yeah, peak lower than the first one. That's good. The peak, although I think that might have been wrong though, because if we think about it, the other one, it's got to be root 2. So the frequency, if you have less mass, then the frequency would be higher, not lower. So if the original peaked at 0.6, I would expect the second driving frequency to be root 2 times that 0.6. So at 0.85 frequency, I think. Yeah. So I think it's just the wrong factor of 2. A wrong factor of root 2 anyway. So unfortunate there, but I think you'll definitely still get the marks for the fact that the amplitude decreases due to the damping. That's the one. Yeah, tricky that. Okay. I promise. Okay, so I've seen this question about the cone. I will come back to the question about the cone. In the meantime, let me just have a better crack at this. Did I? Nope. I want to have a look at this table. I want to have a look at this balloon business. So again, the balloon, when density of the air times the volume of the balloon times g is balanced with the density of the atmosphere times the volume of the balloon times g, that is when this balloon is going to balance. So what did you get given? You got given a table with different temperatures inside and outside the balloon, and the mass of the gas inside and outside the balloon. But the mass of the gas inside would not change, would it? That would just be a fixed one. So I'm not sure what the table would show. The variation of temperature with what? The volume of the balloon wasn't given. The second balloon was on Venus, so we didn't have a G value. It doesn't matter because the G values would cancel. They gave us lots of numbers to find densities with. I wonder if it has to do with pressure equals is it a third rho v squared, or obviously PV equals nRT. I would need to know more about what's in this table and exactly how they get you to work out the densities. But basically, I think that's what you're looking for. The goal is if you got given enough information to work out densities, what you're looking for is it balances when the density of the air equals the density of the atmosphere. That's when balancing happens. So if you were working out densities, that would be the point of that comparison. And method marks, even stating that, I think, should be enough to pick up marks. Also, hopefully, if you found questions that you found difficult, not laboring on them, not spending too much time on them, kind of giving them enough time to give them a valid attempt, but then moving on to better questions if there are better marks available. All right, let me have a look at this cone question. Problem with a cone, all dimensions given, is placed in the path of a beam of light intensity, the force on the cone. Oh, I've seen that before. I've seen that before. I've seen. So this is kind of photoelectric effect stuff. This is treating light as particles, I think. So I think if you're considering, so I've certainly, it's a power. Let me have a think. Oh, I've seen a question like this. What was the solution path? What was the solution path for light? So E equals HF. And so you can get the energy of a photon. And so you can get the power. Oh, why don't we try that? So the intensity. Okay, so what you could do, so you know the photons, right? The photons, E equals HF for a photon. So that way we could work out the energy of a photon, right? Presumably you would need to know the power of the beam, which would tell you the energy per unit time. So you could work out the number of photons hitting the surface per second. I'm wondering, it's probably not power equals force times velocity, but you could, in theory, get a force from that. But because if power is equal to force times velocity, and the intensity power, that means the force would be the power divided by the velocity, where the velocity would be 3 times 10 to the 8, which would get you a force, and then you divide that by area. That could be one way of doing it, or dividing by the area would be the same as intensity over 3 times 10 to the 8. Possibly how they intended that. Not sure how the cone comes into play. That might be to do with angles, to do with intensity. So this could be light intensity rather than it being incident normally. If it's on an angle, then you would need to divide by, given that the cone is a perfect reflector. Yeah, so like light would come in and then bounce off. So you would need to know the angle. Oh, this would very much be a change in momentum then. Where I think the energy, so if we consider the photon to be like a particle, E equals H. So for instance, the de Broglie wavelength is H over the density. So the density is equal to H over lambda. So if you know the wavelength of the light, you can work out the momentum of the light. If you know the angle, and the angle at which it sort of hits the cone, you might be able to do some geometry to work out the change in momentum, and then force's rate of change of momentum. So I think that might be the intended solution path. You can get the momentum of a photon and then do that. And that would be per photon. And then you would, again, need to scale that up for the number of photons hitting per second. And that would kind of give you a sort of pressure. That's insane. You would also, like, that's just wild. All right, coming back to some of these paper 3 questions. Also, if there's more information you want to give me about this one, I'll keep it on the board. We can come back to it. So more on the paper 3. There was a 6 marker on the evolution of massive stars for AQA Astro. that hopefully wasn't too bad. So evolution of massive stars. Obviously, they go through the same initials period of. I assume you mean from main sequence, but in case you mean generally, obviously the nebula comes together under the action of its gravity, increasing the kinetic energy of the particles, increasing the temperature until it starts to glow. Eventually, the density and temperature get high enough that fusion starts, and that's when it becomes main sequence. The outward radiative pressure balances with the inward gravitational pressure. Now for massive ones, once the hydrogen runs out, you start fusing helium and heavier elements up to iron. I think it's the NCO cycle or the OCNCNO. That might be the main one, as opposed to helium smashing together to form something else. But once, so that becomes, it expands, there's the outward radiative pressure increases, it expands a lot, it turns into a red supergiant. When all fusion ends, the core collapses into supernova, and the core then becomes either a neutron star or a black hole, depending on the mass of that core remaining. If it's between 1.4 and 3 solar masses, it's a neutron star. If it's greater than 3 solar masses, it's a black hole. So I think that's what you needed there. Oh, horizontally in the cone. Okay. There was a question at the end of Turning Points, which you think you did well. Heard people found it rough. That's exactly kind of what you want to hear. Okay, I'll come back to the cone question, certainly. Half-life and relativity one. So if half-life and relativity, that makes me think of muon decay, where the important thing about, especially if you're considering relativity, the thing to consider is that the stationary object is the true one within the frame of reference. So the distance between the atmosphere and the surface of the Earth is stationary. So you measure it correctly when you are stationary with it. So the length is the true length, and the length that the muon experiences is relativistically contracted. If we're considering time, then from the muon's perspective, it is the one decaying. So that is the frame of reference that has the true decay time. Because we are moving relative to the muon, we are the ones that experience a relativistic time dilation. So it may have been to do with that. Also talking about black body radiation, but with frequency on the x-axis instead of the wavelength. Interesting. Obviously, a symbol conversion there, using just v equals f lambda, where in this case, v is the speed of light. Hopefully not too bad. Black body radiation curve. What am I expecting for that? I'm guessing that's the Boltzmann distribution. Yeah, you just have to be a little bit thoughtful about that, but that should hopefully have been doable. Oh, sorry, I should have read further about this muon, the half-life and relativity one. It was mostly weird just because it was a hybrid calculation and explain question. Yeah, muon decay, classic. 2 detectors which read a number of muons in a 1 microsecond duration. So that will give you, I suppose, the number of muons that decay in 1 microsecond measured on Earth. Yeah. I won't lie, I don't like those calculations. It asked how the ratio would change comparing relativity and non-relativity approaches and explain why they were different. Okay. I agree with you. The fact that they lumped that all into one question was a bit gross. So using classical, because they do that so that it's because of the relativistic length that you use, or the relativistic time that you use. So that effect of gamma and how it impacts the time, especially if you consider the exponential decay, e to the minus lambda t. The fact that the time is inside an exponential means that when time is affected by gamma, it has an exponential impact on the result. So if you consider relativity, then the muon experience is actually less than 1 microsecond. And so you would get less decay in that time. And so you would expect the ratio to be bigger than if you did Newtonian mechanics. So hopefully they gave you a nice speed that where the gamma was a nice number, and that nice number went into the exponential quite well to kind of work that out. But I think that's the core idea of that question. Some people either only explained or only did the calculations. Yeah, I can kind of agree. Time dilation, yep, all good. Nice, you've locked that in. Yeah, back to the black body radiation question. Yeah, you would expect that the graphs would be the exact opposite way around to the way you'd think they would be. In fact, let me put you over here for a bit. They would be the other way around. You're quite right. When you expect, because frequency and wavelength go in opposite directions on the x-axis. So with frequency, it increases from left to right. The peak would be on the right with frequency, but with wavelength, the peak would be on the left. So it does, but it kind of just mirrors the graph. So hopefully that shouldn't have been too bad. Okay, so yeah. Okay, so we've got. Oh, so going back to the life cycle of stars question. So the 3 bullet points were how black holes are formed. That's post supernova when the mass of the core is above 3 solar masses. The gravity forces it to collapse into a singularity, and it turns into a black hole from which not even light can escape. Second bullet point: why the mass of a black hole is less than the mass of a star. Because it's only the core, as opposed to all the outer layers that get thrown out in the supernova explosion. What happens to massive stars which are not black holes? They form neutron stars instead, where the density is not sufficient to cause it to collapse into a singularity, but it is sufficient to cause the atom to collapse, and you just get neutrons. So it has the same density as a nuclear density. Hopefully that helps. Right, let me come back to this cone question while I wait for any of the other physics questions. So coming back to here, this is where we are at. We have the cone. The dimensions can be used to work out the angle. We know that let me go back and catch up with this. The light came in horizontally. Then you've got your normal, and it's going to bounce off with the same angle. So if we know theta, let me just try and work out which angles correspond to what here. So this here would be 90 minus theta, which means this here would be theta, this here would be 90 minus theta, this angle here would be theta, and this angle here would also be theta. Okay. So you've got that. So during the paper, you were able to think, since the cone is a perfect reflector and light hits it horizontally, the horizontal component of the force will be 0. I think the force, I'm not sure that's correct, because I think the force will be experienced normally to the surface of the cone. So the force parallel to the surface of the cone should be 0, but the force perpendicular should not be 0. So it's almost an oblique collisions question. So light is horizontally, the horizontal component of the force is symmetry. I'm not sure that's correct, though. I think it's to do with the normal versus parallel to the plane. Oh, you're saying there's perfect left, right, and front back symmetry of the cone. Oh, am I getting confused? I'm thinking this is only a single beam. Are you suggesting it's coming from all directions? Oh, you mean this thing is washed in light? That's interesting. Multiple beams. Okay. So then you are right that the horizontal forces. Well, what you need to understand is, because let's consider a single beam. This single beam will be exerting a force in the normal. So it'll be exerting a force like that. If that force exists all the way around the cone, you are right that the horizontal bits would cancel out, but there would be a net downwards force from all of those beams. So beams hit from all sides. You would need to. So force is rate of change in momentum. How do you calculate that? Well, momentum, let's consider it to be mass times velocity. I know that a photon has no mass, but work with me here. The vector change, because it was going like this, it is now going like that, where the angle in between those two is 2 theta. The change in momentum is final minus initial. God, this is complicated. It's certainly above any A-level question. So I'm legitimizing you're finding this difficult. Now, we know that parallel to the plane. Why don't we consider this then? Parallel to the plane, the change in momentum will be 0. Perpendicular to the plane, the change in momentum will not be 0. Perpendicular to the plane, we had, so let's consider the plane's perspective. We had a perpendicular component of v cos theta, and it left again with v cos theta, where the speed has not changed because it is the speed of light. So the change in velocity would be 2v cos theta. And so the change in momentum would be 2mv cos theta, where the initial momentum is just mv. So it would be 2h over lambda times cos theta for an individual photon. It was a high weightage problem. Normal problems are 4 to 5, but this one was 10. So it isn't a must do. If you really can, it helps. I would say also think about getting some method marks, right? So any attempt will get you some marks for what you demonstrate. So as long as you demonstrate some good stuff from the syllabus, I wouldn't be too stressed about that. This is my attempt. I don't know that this is correct, but I think this would be the change in momentum for an individual photon. And then you would need to know the rate at which photons were hitting the cone. And that you could put in, that would give you the rate of change of momentum, which would get you a force. And then dividing that by the area that the light is incident on would get you a pressure. Yeah, so hopefully that helps for, even if it's not, it doesn't help with that specific question. Well, look at the way I went through the thought process. I also found it hard, but it's just like piecing it together slowly but surely. I don't know that that's the correct intended solution path, but given that that test is behind you, now it's about moving forward. How do you improve your problem solving skills more generally? Yeah, it's more comments about the paper 3. So you did OCR. Lots of people are saying it's really easy. You thought it was mid. So now I think if you think you've done badly. Not necessarily. It could be that they've underestimated it. It could be that you've underestimated your own performance. Like if you're very sort of aware of where your strengths and weaknesses lie, maybe that you've kind of overestimated kind of any mistakes that you've made. I would just leave it. Just leave it until results day. Nothing you can do about it now. Ooh, speaking of results day. So when is results day? Results day for you guys for the A level It's the 13th of August. So a couple months out. Almost, yeah, just a little bit under 2 months from when you guys all finish next Thursday. Just going to lock in on math now. 2 papers left. Exactly. Oh, and if you don't have further math, that means you really only have 2 papers left. And also, depending on, like I was saying at the beginning, depending on your board, you really are going to have to lock in for the math, depending on whether you got that Edexcel paper 1. Because that Edexcel paper 1 did not look fun, guys. Oh, but righty-ho. So, yeah, you do Edexcel? Right. You are not having a fun time with this. You are not having fun. Luckily, you're all on the same boat, so your grade boundaries are just going to be lower in math this year. But like I said at the beginning, it means that all of you now are going to be sort of Squid Games fighting for your position on the curve when it comes to paper 2 and paper 3. And yeah, so I think you're right. I think you've got your priorities straight. I think thinking really hard about the checking technique that I've demonstrated, like how you get every available mark that you deserve in paper 2 and paper 3, because you've got less safety net, right? And so it's a bit more high pressure. And so managing the psychology of that as well. I don't want you to go into the paper and then be very nervous, thinking like, oh, is it going to be another hard one, and building up that narrative. So staying on top of your mental game will be very important. Going in, making sure you answer the questions that give you confidence and momentum is going to be top priority. Stay on top of the psychology, get the marks you deserve, learn from the experience of paper 1. I've already seen paper 1 be analyzed on YouTube. So you can kind of get into their heads and think about the problem solving strategies they seem to be leaning into. And you can kind of play that meta game with them. You can obviously also play the meta game with Edexcel of knowing what topics came up and what topics did not come up, and kind of emptying the tank on those topics in paper 2, because you know that paper 3 is just going to be stats and mech. So really consolidating those topics that didn't come up. I know I'm not telling you anything you don't already know here, but yeah, just reinforcing that is the strat. That is the strat to try and do your absolute best in this. And then obviously then paying very close attention to paper 3, things that you might have let yourself slide on in the stats, things like the large data set, things like your sampling methods, and just making sure there's no nasty surprises waiting for you, because you kind of, your nasty surprise budget has already been used up. Right. If no one else has any questions about the physics paper 3, I think I'm happy to leave it there and just say congratulations, guys. You did a physics A level. I think for the rest of the week, I am planning on doing a live solve of the OCR paper 3. I don't yet know when exactly that's going to be. Maybe tomorrow, possibly on Friday. Then I think, well, this is probably going to be, because so I've been using these shorter streams to just consider the physics, right? Do a sort of physics seminar. You've done physics, so there's not going to be much more of that. So I think I'll do one more next week as a kind of debrief of math paper 2. I don't think I'm going to have time in the evening on the 18th to go over how paper 3 went. And by that point, I think all of you are just going to be off enjoying your summer anyway. So I think I'll do one more of these sort of like live chat interview streams on a Tuesday or Wednesday of next week to go over how paper 2 went and consolidate math paper 3. And then we're done with the exam season, guys. You've got like 10 days left. 10 days to freedom. I know. And like, by this point, you guys are a bit tired. It's like, oh my God, just end already, especially because the papers are like not as frequent as they were. You've gone through like your big week. Yeah, for the math stats this Friday too, like you're getting to that point, but you're also going to be seeing the summer on the other side of the exams, and just keep at it, keep focused, push all the way through the line. So I'll check in with you guys next week to make sure you guys are doing that okay. And in the meantime, I'm going to leave. Oh, you're saying this week is rough for you. 3 tests still to go. Is that Kevin, math and further math? Another 2 next week. All right. But in the meantime, I'm going to leave it in your very, very capable hands. And I'll see you guys next week. Alrighty then. Good luck with all of your tests happening this week. And I'll keep you guys posted. So keep calm, carry on, do good work, and I'll see you next time. All right. Thanks very much. See you guys. Bye-bye.